Yes.
Okay, thank you. So welcome to session Cryptanalysis 2. So my name is Mitsugu Iwamoto. I'm co-chairing this session with Krystian. So we have 5 talks, and we will have Q&A time after each talk. So if you have questions during the talk, so please use the Zoom or chat box. Okay, so the first talk is convexity of division property transitions, theory, algorithm, and compact models by Aleksei Udovenko. He will give a talk. Okay.
Thank you, Mitsugu, for the introduction. I'll just share my screen. So yeah, let me start my talk. First, I would like to provide a very quick high-level overview of the work. The work studies division property, which is a cryptanalysis technique for symmetric ciphers. There are many variants of division property, and this work focuses on the earliest and the most widely applicable one, bit-based two-subset division property, also called traditional or conventional division property. It was introduced by Todo at Eurocrypt 2015. The contributions of our work include new theoretic insights, such as close links of division property with graphs of analyzed functions, and a new compact representation, suitable for modeling larger S-boxes by SAT solvers. In addition, we describe new algorithms for computing propagation tables and compact representations in quadratic time, improving previous cubic time approaches. As a proof of concept, we studied the super S-box model of LED, which was impractical by previous methods and was challenged in recent work of Gerbes and Fouque. In this short presentation, I will focus mainly on the compact representation. Now I will briefly introduce division property. Consider a cryptographic primitive built from iterations of a simple round function. In integral cryptanalysis, we want to know whether the multivariate polynomial expression of an output bit may contain a chosen monomial of the input variables. If the presence of the monomial does not depend on the involved secret keys, we obtain a distinguisher from a random function, which can be used to attack the primitive. The core idea of division property is very simple. Consider this example. In order for y0 as a function of x to contain the monomial x0, x1, x2, there must exist a sequence of monomials in each intermediate state, such that at each step, the product of functions defined by the output monomial contains the input monomial. Such a sequence is called a division trail, and they are searched using SAT or SMT solvers or MLP optimizers. To handle the secret keys being stored between the round functions in a simple way, traditional division property relaxes the propagation rule to allow smaller products of output bits to contain larger products of input variables at each step. Then we can ignore the secret keys. For example, we consider this transition valid if, say, Z1 instead of Z1, Z3 contains monomial x0, x1, x2, x5 instead of just x0, x1, x2. And here we consider the function f0 itself and not the secret key. In order to use SAT, SMT, or MLP solvers to find trails, we need to encode possible steps of the trail. The classic approach is to compute full propagation table, where for each input vector, we list all possible output vectors, and then to encode this table in some way. Because of the monotonicity of division property, which is exactly due to this ability to remove or add variables from monomials, for possible outputs, we consider only minimal vectors, or also called reduced vectors. This significantly reduces the table size, but we are still limited by the exponential number of inputs. And here is the key observation of our work. If you consider the full set of reduced transitions, that is pairs of input-output vectors of valid transitions with minimal outputs, we can show that this set is convex, meaning that it has two monotone bounds, the upper bound and the lower bound. This is explained by this ability to add or remove variables from monomials. And what's important about convexity is that it lends itself nicely to CNF encodings to be used in a SAT solver. More precisely, the CNF formulas have size depending on size of these two boundaries, rather on the size of the full set itself. While it is not guaranteed that the representation is always small, it is usually much smaller than the full table. Here are some examples on model sizes of some S-boxes obtained using our technique. On medium-sized S-boxes, such as the AS S-box, we can see that our method produces a bit more constraints than the optimal encoding. The problem with the optimal encoding is that it doesn't scale well and quickly becomes infeasible to obtain for larger S-boxes. We can model 16-bit super S-boxes with varying success. For example, LED's super S-box can be modeled by about 300,000 constraints, while weaker Midori's super S-box requires 2 million. For modern solvers, it may be still in the feasible range, but it really depends on the exact setup. An interesting case is the heavy linear layer of LED, which is based on an MDS matrix. It was the source of problems in the work by Derbez and Fug. Using our method, it can be modeled by just 30,000 constraints. To conclude, please look for more results in the paper and check the code repository, which has convenient implementations of the described techniques. And please look at the interesting problems left. And this concludes my talk. Thank you, and I'll be happy to answer your questions.
Hey, thank you very much for your talk. So do you have any questions or comments? So if you have questions, please use the Zurich or chat box, or raise your hand virtually and talk by muting yourself.
So maybe I'll start with a question in the longer version of your talk, the recorded one, right? I think that was slide 5 here and slide 12 in this. Yeah, right. So over there you said something like more complex transition structure may somehow indicate algebraic weakness of the S-box, right? Is this some, did I get it right? Do you think that this could be used as some sort of a quick test that I have this new S-box and then I can run this and see, oh, this looks much bigger than I would expect, and then perhaps there is something deeper there and I can it's worth studying it?
Yes, it can be, but it's not very direct. For example, we can look at LED's a linear layer, so it's linear, so it's not algebraically. It has degree 1, and it has very compact representation here. So in this way, you cannot say it's very weak, while it's weak because it's linear. But if you will say have some degree, like you have, for example, if you compare AS and MIST AS boxes, you can see that AS's box is has much more compact representation than MIST, and we know that MIST has these weaknesses that allowed integral attack.
All right, thanks.
Okay, thank you. So if you have another questions or comments?
You can also unmute yourself and ask the question directly if you prefer.
Okay, thank you very much for your talk. So let me do the second talk.
Thanks.
So yeah, thank you. The second talk is strong and tight security guarantees against integral distinguishers. The authors are Phil Hebborn, Baptiste Lambin, Gregor, Leander, and Yosuke Todo. And Baptiste will give a talk. Please start.
Thanks for the introduction. So yeah, today we talk about strong and tight security guarantees against integral distinguishers. So the main topic is integral attacks on block ciphers. So a very generic way of seeing these attacks is that we need to find a set M of plain text such that for any key, if the sum of the corresponding cipher text is always equal to 0, which probability 1, and no matter the value of the key. So this is something we would not want for an ideal block cipher. So this leads to a distinguisher, which leads to an attack. And so we would like to be able to give arguments on whether or not a given block cipher is secure against these attacks. And well, if you follow the generic idea, then this would mean showing that there is no such set M of plain text. So this looks a bit complicated, but if we take a closer look at the block cipher, we can see how we can eliminate at least some integral attacks for now. So let's take a look at the ANF of our block cipher. So it's a way to represent block cipher as a keyed Boolean function, so as a sum of some vector of polynomials pu, which depend on the key times some monomials xu. And using this ANF, we can define the algebraic degree, which is maximum of all amit weights of u, so that pu is not zero, basically just the highest degree of any monomial xu in the ANF. And the reason why this degree is interesting is that it's well known that if the degree is too low, then we get integral attacks. And so the first step to show that we have no integral attacks would be to show that the degree is high enough. And this requires to give lower bound on this degree. And well, we did that last year at Asiacrypt with the same author. We gave for the first time some lower bound on the degree of block ciphers. And the way we did this in a very short summary is that if we expand the key polynomials pu as the sum of some lambda uv times kv, you can show that this block cipher is of degree d if you can find the u of amit weight d, so that at least one lambda uv is non-zero, which means that there is this monomial xu of degree d, so the cipher is at least of degree d. And what we did in this paper last year was to essentially show how we can choose which lambda uv to focus on, so that we can actually compute this lambda uv in practical time, and just showing some lower bound on the algebraic degree as well as some stronger properties. However, we still had some issues because it only proved resistance against the subset of integral attack, not actual resistance. And in addition to still being quite expensive in terms of computations, the bounds we gave were also only true for a given number of rounds without any guarantees on more rounds, which is a bit disappointing when you think about block ciphers. So in our paper this year, we address these three problems, and today I will only focus on the first one, and I encourage you to either watch the full video or read the paper for more details. So the main observation we made is that if there is an integral distinguisher, so if there is a set M so that the sum of ciphertext is equal to 0, it actually means that the key polynomials pu are linear dependent. So if we want to show security, we need to show that all of these 2 to the n functions pu are linear independent, which when n is at least 64 for modern block cipher seems very hard to do. So what we showed is that under a few assumptions, so having independent round keys like in our paper last year, as well as adding a whitening key, we can reduce the problem from 2 to the n linear independent polynomials to only n squared polynomials, where just some specific polynomials speak for some specific value of the vector. So the vectors ei, which are equal to 1 everywhere except in one coordinate. And so now we only need to show that n squared polynomials are linearly independent, which means we only need to compute about n squared coefficient lambda for each polynomial. So in short, assuming independent round keys for a given block cipher, we only need to compute about n to the 4 well-chosen coefficient lambda uv. And we want to, by doing so, we want to show that these polynomials are linear independent. And if we are able to do so, then by adding a whitening key to the block cipher, this augmented block cipher is actually resistant against integral attacks. And so this n to the 4 is quite a bit more work compared to our work last year. So we had to improve a bit the computational side by improving the heuristics we used. And we also show that if it's integral resistant on a given number of rounds, it's also resistant for any higher number of rounds. It's not true in general for algebraic degree and minimum degree, but in the paper we showed when this is actually the case. So to give an overview of the results, here are the block ciphers we studied. And in red, you can show the cases where the bounds are tight, meaning the number of rounds we prove to be resistant matches n+1 when n is the highest number of rounds we can attack with integral attacks. And in the case of Git and present, it doesn't mean that, for example, we can find an attack on 11 rounds of Git. It means that computationally, we were not able to show that 11 rounds is resistant or not. So there is still some margin to improve here. And overall, we would like to, well, improve this method, making it faster, improve the heuristic and better understand these heuristics, and also making it more usable and more versatile, because for now, it still requires a bit of tweaking for each block cipher. So thank you for your attention, and if you have any question.
Okay. Thank you very much for your talk. So we have a question from in the chat box. So do you have some ideas about how to process the permutation-based ciphers which loads the keys at the beginning?
It's also part of the future work. It's very hard with the current framework because we rely on having the so this hypothesis of having independent round keys allow us to simplify the problem a bit, because computing this lambda UVs comes down to counting the number of threads to an MAP problem, the number of solutions to an MAP problem, which is very hard in general. And having these round keys allow us to a bit control this number of solutions, so that way you can make it low and actually count them. So for permutation-based crypto, we don't have these round keys. So if, for example, there are 2 to the 32 threads to enumerate, well, we have to do it, and we cannot control lower. So for now, immediately, no, I don't really know, but it's part of the future work for this project. I mean, this topic, let's say.
Okay, thank you. So the next question is that is this method potential to extend to prove balanced integral sum?
Sorry, can you repeat that? Is it in the chat?
Yes,
Okay, so
in the
to
chat.
improve,
Yeah.
to prove a balanced integral sum. So technically, you can use this to, since you can compute the lambda UVs, so the coefficients in the key polynomials of the ANF, you could theoretically try to show that a given key polynomial is 0, meaning that the given monomial X2 does not appear in the ANF. In practice, this is quite hard because it's much easier to show that these polynomials are non-zero by showing that at least one coefficient is non-zero, and showing that these polynomials are equal to 0, which means showing that every coefficient is equal to 0. So it looks rather hard, and if you can still use, so it's based on division property. I encourage you to check the Eurocrypt last year paper by et al, I think. That introduced so this division property with 3 subsets without a non-subset. And if you just use it without, in a bit of a weaker way, you can still show some distinguishers by, because some cases you can show that there is no trail. Maybe I can ask, I can answer that in more detail from Zulu. If you want more details, let me know. Thank you.
Okay, thank you. So do you have any other comments, questions?
So I have one more question.
Yes, please.
If I understand this paper correctly, then you use this assumption that you have addition of independent round keys. And my question is, okay, what happens if the round key added at each round is smaller than the internal state of the round? So basically, we don't do a full XOR, but something less than that. Does it complicate things? Could this be extended to cover this case?
So it's, for example, it's a case for skinny and give. So in our case, indeed, we added the key over the full state, while for skinny and give, the keys only added on half a state.
Right.
So the idea can be translated immediately. If you still assume that they are independent, because handling the key schedule is a bit complicated, but
right.
If you still assume that they are independent, the algorithm works basically the same. You just like it's not even super hard to change in our implementation. You fix some value for the division property to be 0, basically. The issue is that it gives us a lot less control on the number of trails, on the number of solutions to this MILP problem. So it's likely to be much harder to do. And we did not have time to experiment too much with this. I think it's something we could probably try. It shouldn't be like it's not very hard to adapt, but in terms of computation time, it's likely to make the problem quite a lot more complicated.
All right, thank you.
Okay, thank you very much. So let's move to the third talk. The third talk is entitled Massive Superpoly Recovery with Nested Monomial Predictions. So the authors are Kai-Hu, Xuan-Sun, Yosuke Todo, Meiqin Wang, and Qingju Wang. The speaker is Kai-Hu. Okay, please go ahead.
Thank you for the introduction. And my name is Kai-Hu, and this paper is called Massive Superpoly Recovery with Nested Monomial Predictions. And this is the joint work with Siwei Sun, Yosuke Todo, Meiqin Wang, and Qingju Wang. Qubitac was proposed by Leander and Xavier and Europe 29. And given a polynomial, we can focus on the coefficient of a so-called cube term. And this superpoly and this polynomial is called superpoly, and it will be simpler than the original polynomial. And for any output bit of a symmetric cipher, the superpoly is a function of k and non-cube variables. And if we let the non-cube variables at 0, then the superpoly will be a pure polynomial of only k variables. So if we know the NF of the superpoly, we can get some information of the key variables. And so recovering the NF of the superpoly is a core problem in Qubitac. Division property was proposed by Todo and Eurocrypto 2015 and introduced to the Qubitac and Crypto 2017. And the monomial prediction is another language explaining the division property from a polynomial perspective. Given a composite Borel function y equals fx, the monomial prediction or division property can predict if xu, this term, does or doesn't appear in the polynomial of this term by counting the monomial or division trials. So given a cube term, if we can find all the gk times x to u, then sum them together, we can get the final superpoly. However, the previous method has some challenges. As the number of rounds of cipher increases, the superpolies become more and more complicated. The previous method cannot work. Actually, we took directly the monomial prediction to recover the superpoly for 843 round trivial. No results are obtained for a month. In this paper, we give a new nested framework with monomial prediction, which is efficient for massive superpolies. Of course, it works very well for simple superpolies. And given output of a stream cipher, we firstly choose a positive R0 and express f as a polynomial of the internal states here. And then we construct MLP models for each term in this polynomial. Different from the previous method, we need to add a time limit tau to this MLP model. This is easy in Groovy solver, for example. And then after the time is up, all terms in this polynomial can be grouped into 3 disjoint sets. The first set contains the monomials which are solved but infeasible. So we know these terms have no contribution to the final superpoly. And the second term contains those terms which are solved and feasible. So we can extract some partial superpoly from this term. And the second set contains those monomials which are not solved within the time limit. So we have to proceed this set in the following step, and this set is called undetermined set. And in the for this set, this step, we can recover a part of the superpolies. So in the next step, we expand the polynomial, the monomials in this undetermined set to another deeper internal states other polynomial. Yeah. And then repeat the process to construct the MLP model with a time limit, and then discard some monomials and collect some part of the superpoly, and until the undetermined set is empty, and then we can collect all the partial polynomials along the way, and then we can assemble them to final superpoly. And here is a application to trivial, and the table shows the 5 cubes we used for the trivial up to 845 rounds, and these cubes are chosen just by just adding index to a previous cube. So these cubes are chosen very carefully. Here are some detailed information of the superpolies we recovered for cubes I introduced just now. And you can see the trials, the division trials are many, and the terms are also huge. And this superpoly can recover within about 3 weeks. And this is the result for grade 1 to 8. And we also recover improved superpolies for trivial. So with the recovered superpolies, we can do the key recovery attack. However, because our superpolies are very complicated and involving all the key bits, so simple exhaustive method cannot work anymore because the complexity will surpass 2 to n. So as is well known, Mobius transform can transform the NF of a Born function to its truth table, or transform the truth table to its NF with n times 2 minus n to 2 minus n minus 1 XOR. And also notes that our superpolies, although they are very complicated, but they are still sparse compared to a randomly chosen polynomials. So a fine grade analysis can upbound the complexity to n times 2 to n minus 2 XORs. And then we can use the Mobius transform and with the divided and conquer strategy to do the key recovery attack. And we introduce a new concept called disjoint set given a superpoly PK. If Ki and Kj are two variables in this superpoly, are never multiplied together, and we say Ki and Kj are disjoint if for a subset of variables D, and every pair of variables are disjoint, we say D is a disjoint set. And given n superpolies P0 until Pn minus 1, and if D is the disjoint set for each superpoly, we call D is the common disjoint set of these superpolies. Then, given if PK has a disjoint set D with m variables, and we can write the polynomial in this form. And the Pij and the Pmj are involved at most n minus m variables, and then we can use the Mobius transform to construct the truth table for Pij and the Pmj. So with the m+1 truth tables, we can access them and get the values for each key combination in J, and then this equation will become a linear equation. Then with the linear equation, we can recover some key information easier. And this table shows the key recovery attacks in this paper, and they are improved according to the rounds. So in this paper, we give a new efficient framework with nested monomial prediction for massive superpoly recovery. And we also give a new key recovery attack strategy with Mobius transform based on massive superpolies. We also give some improved key recovery attacks on Trivium grade 1 to 8A and Trivium. Thank you for your attention. That's all.
Okay, thank you very much for your talk. So we can have a short question. So if you have any questions or comments.
So I have one quick question. This time limit tau 0. So could you maybe quickly elaborate, what's the optimum strategy of choosing those time limits for those, subsequent layers of the nested framework?
Yes. Actually, we have some detailed explanation of the intuition to choose the time limit in our paper, but here time is limited, so I cannot show it. Usually speaking, when for the higher round, for example, we attack the 845 rounds, then with the first expanding, we tend to choose a smaller time limit because the round is high, the number of rounds is high, so we don't expect to solve many models. So if we set a bigger time limit, then it is very likely that this time are all wasted because the number of rounds is high, so it is very difficult to expand to evaluate the partial superpoly. But as the rounds gets smaller, and then we gradually enlarge the time limit, because as the rounds become smaller, the number of terms in the polynomials become more and more and more. So we want to solve as many as possible terms in each step. So we will choose a bigger time limit. Yeah, this is the strategy.
All right, thank you very much.
Thank you.
Okay, thank you very much for so let's go to the first talk. So I would like to hand over the chair to Krystian.
That's right, thank you very much. So our next talk is quantum linearization attacks. And
yes.
And let's wait for
so you should be able to see my slides.
So we can see your screen, and now we can see your slides. Perfect, that's right. So this talk and this presentation is by Xavier Bonnetain, Gaëtan Leurent, María Naya-Plasencia, and André Schrottenloher. Hopefully I pronounce this close enough. And then André is going to give the talk.
Thanks a lot. So yes, as the title says, this is the only talk in this session, I think, which is about quantum attacks, actually. So the model of quantum attacker that we're going to consider here is even more specific. We're considering quantum attacks in the superposition model. So imagine an adversary that can make quantum computations. And then during these computations, the adversary can make a query to, in our case, a MAC, so a message authentication code, which has inputs of multiple blocks. And these queries can be made in superposition over the inputs. So you can consider this MAC oracle as a quantum component from the, which is, yes, as a quantum component inside the adversary's computations. This is a very strong model, but it's known that there are attacks in this model that we don't have with classical queries. And this is what we're going to do here. And on this attack, our goal is to forge tags. So these are forgery attacks. And we're just going to say that this means that the adversary in the end of these computations is able to output more valid message MAC pairs than the total number of MAC queries that the adversary made. Okay, so you have this computation making a number of superposition queries, and then in the end outputting many tags. So typically in superposition attacks, we use structure finding tools, dedicated quantum algorithms to find hidden structures. A typical tool for that is Simon's algorithm. Actually, it's also one of the tools that we use in our paper. The Simon's problem is the following. If you have a function that is either injective or that has a period, and this is a Boolean period, so it means that x and x XOR s for this period s always has the same image. Now, if you have that, then you can recover the period very easily with a quantum algorithm that makes superposition queries to f. So it's done in polynomial time. And classically, of course, if you don't have any other information about f, it will cost you an exponential time. And it works in the crypto context, even if f is a random function, with the promise that it has periods. So typically what we do in these superposition attacks is we have a function that has a very strong algebraic structure, like a block cipher construction or a MAC construction. And we have this oracle with a secret key k. I want to recover something about the secret. So what we do is we define a periodic function from this. So we take the output of our black box ek, and then we do some post computation on it, and this becomes a periodic function. And then we use Simon's algorithm. So of course, Simon's algorithm requires superposition queries, so we do superposition queries. But you can imagine that in general, this approach needs to have at some point in this structured function a XOR between some secret value that we're going to recover, that is our secret period, and some input of the black box that we need to control, that the adversary needs to be able to put into superposition. This is what happened in most, or let's say all the previous attacks in this model. Now in this paper, what we show is that you can do things a bit differently to target some new symmetric constructions. In particular, these are a certain number of MACs, parallel MAC constructions that you can attack using Simon's algorithm, but also different quantum algorithms like Deutsch, Benson-Vezirani, and Scholz. And there is a long list of MACs that are attacked, so I'm just going to cite some of them. Light MAC plus, and also beyond birthday bound variants of them. And also we have like a new superposition attack on Poly 105. So how does it work? So I'm going to take a very generic example of this. And you can see, since it's very generic, there are many constructions that fall into this depiction. So let's say you take secret dependent functions with these permutations by I here and a function f here. And the adversary doesn't access these components. He only has access to the MAC, the whole MAC. And the goal is to forge tags, right? So on this construction, you can't, well, you don't have XOR between a message and a secret. And this is what we're going to attack. So this function MAC is not periodic. But what we're going to do is to create another function, create a restriction on the inputs, such that the MAC restricted to the inputs becomes periodic. And in order to do that, we just take two values for each block. So each block is going to depend on one bit only. And now you make this a function of an input of L bits, because there were L blocks. And you can remark that this function is basically the output computation of some sum, which depends on the L blocks. And this sum inside is an affine function, because each time you flip a bit, you simply XOR something to it. Okay, so we have some post-processing of an affine function of our input. And well, an affine function is periodic. As long as L is large enough, actually there are periods that appear inside in this affine XOR. And so these periods become periods of the whole MAC function. So by doing this, so by restricting our inputs, we're able to create a periodic function. And actually, once we recover these periods, we can use it to forge as many tags as we want. So this generalizes nicely to beyond birthday bound variants, because if you have like what usually happens is that instead of having a single sum, in the end you have multiple of them, and you can do that for all the sums in parallel. So you can use the same technique. So what happens really is that if you process all the input blocks independently and you compute a XOR of these blocks or anything that is linear, and you compute the tag out of that, then you're exposed to this kind of attack. So you can see this really from a cryptanalysis perspective. It means that we're able to break in the superposition model, of course, many MACs. From a probable security perspective, it means that, well, it's an interesting question to know how we could overcome this, to be able to compute, to create secure designs, and in that case, secure parallelizable quantum pseudo-random functions. And we also don't know if this has consequences when you make only classical queries, so that's an interesting open question. Thank you for your attention.
Thank you very much. Thank you for the talk. And now time maybe for one or two quick questions in the chat or Zulip. So while we wait, maybe I'll start with one. So I have a question about this combining function, right? So you said that, okay, for everything that is linear, that's actually insecure. But I think in the longer version of the talk, you mentioned that modular addition, for example, that the case is not clear what we can do. So do you have any other intuitions of the split between those that are definitely vulnerable to the attack, like linear functions, and then those that maybe are okay, and then those that you are kind of reasonably confident that they should be fine?
Well, we know, for example, that if you have not a parallel but a sequential MAC, like HMAC and NMAC, they are secure. So so because in these MACs, actually, you don't process, or you don't sum everything in parallel, but you have like a compression function that processes each block sequentially. For modular additions, I really don't know. Like it just happens that you need XORs here because you need some kind of involution. And I really don't know if you can prove something with modular additions. I think it would be a great result, but it might be extremely hard as well, just because the only problem with them is really that they're not involutive and the attack just doesn't work. But that doesn't mean like there is an easy way to prove that. Yeah, apart from that, like I don't really know. I don't really know what would be a really good secure design.
All right, thank you. That's interesting. Any other quick question? If not, you can always put a question in Zulip, and hopefully the authors can answer offline.
Sorry, can I ask a question?
Sure, go ahead.
André, did you consider Farfalle? Because it has kind of similar structure, but maybe a bit different.
Yes. So we didn't specifically consider that. So I think that the problem with Farfalle, so to say, is so in Farfalle, right? You have several message blocks. You process all of them. Indeed, you have a XOR of everything, and then you expand a bit the output, I guess. But what happens is, for example, if you reduce this to a single block, then I think specifically in the Farfalle construction, you already have like a XOR between message and key somewhere, or XOR between message and secret, and you can already attack this with some algorithm. So actually, I think you didn't need the linearization attack to do that. My guess is you could use the linearization if you wanted to attack some kind of generalization of Farfalle. That would look a bit like this construction on this slide. But yes, I think the main problem is that there is actually already an attack in this superposition setting. So we don't have anything new there.
Okay, I see. Thank you.
Thank you very much. I'm looking at the time, and I think we need to move on to the next talk. So thank you again. And yeah, if you have any questions to André, then put them in the chat. All right, so let's move on to our next talk, and the last talk of this session. It's going to be generic framework for key guessing improvements by Marek Broll, Federico Canale, Antonio Florez-Gutierrez, Gregor Leander, and María Naya-Plasencia. And Marek is going to give the talk. Please go ahead.
Thank you very much for the introduction. In this paper, we improve the key recovery part of various attacks against SPN ciphers by looking at the S boxes and deriving special key guessing strategies for those S boxes and related functions. Let's say we are given a cipher which is subdivided into 3 parts. Then in a usual key recovery attack, we are given a certain set of plaintext ciphertext pairs and try to guess key material on the outer part of the cipher to derive states around the middle part of the cipher. Then we apply a distinguisher which can discriminate between the right key guesses and the wrong key guesses. And in this paper, we only look at the key recovery part and optimize that the guessing strategy for that. We have 2 main observations. The first observation is that the distinguisher doesn't need all of A and B, and therefore we don't need to guess all of the outer key material K0 and K2. This also holds inside S boxes. So if we only need a few output bits of an S box, then this does not depend on all of the input bits. Our second observation is that even if we do need to guess every key bit, we usually can cut the computation short because after a partial key guess, the relevant output bit is already fully determined. We'll illustrate this with the following example. We are given a plaintext M, we add some key material, then apply a 4-bit S box, and we are interested in the last output bit. Instead of guessing the key, we can also just guess the direct input to the S box, which is in this case then M plus K, and we'll denote it by X. Here you see we did this for the Meiqin S box, and on the right you see the guessing strategy in form of a tree. You start at the root label and guess the linear combination of the bits indicated by that label. If it's 0, you go left. If it's non-zero, you go right. And at some point you will arrive in a leaf, and that's the desired output bit. Note that the output doesn't have to be a bit, it can also be a binary vector. If we had guessed naively, we would have needed 16 guesses in total. But from the tree, we already see the function only ever depends on x0, x1, and x2. Therefore, we can do with 8 instead of 16 guesses. And from the tree, we also see that we don't have to guess all 3 bits. In the left branch, we only have to guess x0 and x1. In the right branch, we only have to guess x1 and the linear combination of x0 and x2. And therefore, we can do with 4 guesses. This is no coincidence, because we could show in the paper that in many instances the complexity of the guessing strategy is directly related to the number of leaves of a corresponding tree. In this case, we gain a factor of 4, but we can also apply this technique to more than one S box and then further increase the gain. Another trick that we've introduced is key absorption. I won't go into details here, but basically it allows us to join certain key guesses in subsequent rounds into a single guess, and then by that reducing the number of guesses in total. For more details, please consult our paper on that. Our attack can be applied to our methods can be applied to many types of attacks. For example, we applied it to a linear attack against Meiqin, to a rectangle attack against gift, to a differential attack against rectangle, and to a sieve in the middle attack against present. The last one is noteworthy because it's neither a linear type nor a differential type attack. Thank you very much for listening. If you're interested in further details, please look at our paper on ePrint.
Thank you very much for your talk. And I see that we actually have 2 very specific questions in the Zoom chat. So let me read the first one. In the description of the boomerang attack on rectangle 80, step 1, you said, just as an example, in order to guess the relevant key material for S box 7, we can compute both the good pairs and the linear relations for the active output bit y0, necessary for the key absorption in step 2, with an average number of key guesses 2 times 1/8 plus 7 times 7/8 is equal to 2 to the power 2.73. I want to know what does the 7 times 7/8 mean here? How can you get the number 7? So if you can read the chat, as a Zulip chat, right?
I can't read the Zulip chat because I'm not logged in there.
Oh, okay. So, well, okay, it's a bit specific question, and here it is. Thank you.
Here it is. Thanks. I can't answer the question from the top of my head. I'm sorry.
Right. So I think that it would maybe make sense to just chat offline and then explain this. It's a bit specific. I don't know what
think
about
it and write it in the Zulip chat. But if I forget, please drop us an email. Then we'll answer that question.
That makes sense. And then I think that the second question is also pretty specific because it asks about the derivation of complexity in appendix E2, right? So that might be probably also hard to answer right now. Just one quick question from me. So you said that one of those strategies is the key absorption strategy. Do you think that this can be somehow combined with the knowledge of the key schedule, and then this could improve somehow those attacks?
Theoretically, yes, because I mean the key guessing. So the key absorption more in detail works like this. You have to your last guess, the last guess that you do for a certain bit that you need in the second round, can just be written as an can just be written as a additive term to a nonlinear function and then to the next key guess that you need. And if you have if you use the key schedule there, then you might see relations between single key bits in the key schedule. Therefore, I would think it might be possible, but it would be probably involved to look at this.
All right, thank you. I think we are running out of time, so if there are no other questions, then thank you again for the talk, and I'm turning it back to Mitsuru to close the session.
Okay, thank you very much for Krystian. So I would like to close the session. Thank you very much for the speakers, and thank you very much for audiences to join the session and discussions. Okay, thank you very much. So please enjoy the last session in the Asiacrypt, starting within 38 minutes. Okay. Thank you very much for joining.
Thank you very much to everyone. Thanks.
Thank you. Thank you.